Hello, everybody. So my name is Roger Artigas. I'm CTO of Sensofar, and today I will be explaining about the interferometry technology that we use in our systems. And that interferometry technology, we are using it in two different cases. One is three-dimensional measurement of technical surfaces. The other way we use it is for the measurement of transparent materials to measure the thickness of both thin and thick films. So let's introduce to you a little bit the technologies we use at Sensofar and the portfolio of the products which are using that technologies. This is a subject that we are covering these days with other webinars, but just to refresh you a little bit. So we use confocal, active illumination, focus variation, interferometry, and fringe projection technology. And also we use thick film measurements using confocal and interferometry, and spectroscopic reflectometry for the measurement of thin films. The three first technologies, confocal, focus variation, and interferometry, are the three ones that we can combine in a single instrument, a single measuring sensor head. Fringe projection is not able to be combined with these three technologies, and that's the purpose for dedicated instrument for that. So that's the portfolio we have Sensofar for the tabletop systems. On the left is the one using fringe projection that we were covering on the past on a different webinar. The other systems are using the combination of these three technologies or four technologies in the same instrument. And also we have a portfolio of integrable sensor heads using also single technology or multiple technologies in the same system. So the purpose of integrable sensor heads is the integration of that three-dimensional measuring technologies into your process. It could be in a quality control environment, can be an in-situ quality control environment. It doesn't matter. The point is that you have a full SDK. You can completely program that systems to measure the three-dimensional surface by your own. So, okay, let's talk today about interferometry. So what's that? So interferometry is, probably would say that is the most precise measuring technology coming from physics. Is a technology that is used to measure a lot of things. We can measure three-dimensional topographies like I will be covering today, but with interferometry we can also measure the distance from Earth to the moon, or from our solar system to other stars on the galaxy. So you can cover a huge dynamic range. You can measure so long distances like stars, and also you can measure very, very close distances like atomic scales. So independently on the final configuration of an interferometer, we always have a schematic that is very, very similar to the one we are seeing now on this slide. So we have a light source that is in somehow collimated into a beam splitter. The beam splitter splits like in two, typically is 50 by 50. One is going to what is called the reference mirror. In that case, is the green light going to the top. And then we have the other portion of the light going to the sample we want to measure. So what happens on that thing is that the light is traveling along this space, and it could be that the time needed to travel from the beam splitter to the reference mirror, or from the beam splitter to the measuring sample, is not exactly the same time. And that time will be the one responsible to create some intensity changes on the detector we will see at the end of the light path. So what happens from the mathematical point of view is that, don't be scared about the equations on that slide. They are extremely simple. So there is something that we call the OPD. The OPD means the optical path distance, and equals to the difference in length between the beam splitter and the reference mirror, and the beam splitter to the measuring sample. This needs to be multiplied by the n that equals to the refraction index, that most of the times n equals to 1, because we are dealing with air samples, or samples that are located on air, not on liquids or not on other kinds of materials. So the OPD that is measured in microns or nanometers or meters, it doesn't matter, it's a distance measurement. it's converted to a phase distance. And to convert that, what we do is to multiply that by 2 pi and divide by the wavelength of the light we are using. And finally, the intensity we will be receiving at our detector will equal to the equation at the end, that is what we call the I prima, that is the background intensity, and I second prima, that is the modulation multiplied by the cosine of the phase difference. So just for better understanding, what does it mean? So imagine we have a sample that is tilted with a given angle in respect to the optical axis. And then we have a reference mirror that is the one on the top of that slide that is completely perpendicular to the optical axis. So what will happen is that there are portions of that sample that will have optical path difference to the beam splitter to the reference mirror that are exactly the same quantity multiplied by 2 pi. So that, and we have to go back to that equation here, the middle one. So what will happen is that the light time travel from the beam splitter to the sample for the white part of the bars is exactly the same multiplied by lambda over 2. And what happens in middle? So the dark bar with the white bars, it means that the height tilt, so the time travel between the reference mirror and the sample equals to lambda over 4. So by just only tilting the sample we want to measure and counting by just using your finger the number of fringes you are seeing here, we can tell you how much height there is in total onto that sample. So every time it goes from white to white equals to lambda over 2. So imagine you have a lambda that is 500 nanometers that belongs to light green, close to the cyan blue light. Lambda over 2 means 250 nanometers. So 1, 2, 3, 4, 5, 6 means that we have 1.2 microns peak to eye on that tilted sample in particular. So how to achieve an interferometer for microscope purposes? So that is the slide we are seeing here are the two typical optical configurations for interferometers for the microscope range. The one on the left is called the Michelson interferometer. The one on the right is called the mirror. So the difference between the two is that the Michelson is using a very low magnification microscope objectives, in which the working distance between the optical elements and the sample we are inspecting is very large, and we have sufficient room to place optical components in middle. So in that case, the beam splitter that we were talking before is placed with the optics in the sample, and we have a reference mirror just placed to the right. In contrast, if we increase the magnification of the microscope objective, what happens is that the working distance is very, very small, and there is now sufficient room to locate there, to place there the optical components, like the cube beam splitter before. So in that case, the beam splitter is placed just at middle way between the last optical element and the measuring sample, and is a plain beam splitter. And then we have a reference mirror that is placed just inside. So typically 10x to 100x magnifications can be achieved with that configuration, and the numerical aperture can be much higher than the previous ones, the Michelson interferometers. So okay, so depending on the properties of the light source, we will be dealing with two kinds of different interferometers. We call them the phase shifting interferometer and the coherence scanning interferometer. The phase shifting, the one in the top, is the one that is using the monochromatic light source. On Sensofar systems, this is because we have monochromatic LEDs inside the systems, the microscopes, and we are able to use the red, green, or blue LEDs to perform the phase shifting interferometer that I will be explaining in the following slides. In contrast, if we use white light, that it comes from a white light LED, what happens is that because of the properties of the light source, the interferences looks like the one we are seeing here, and then we use completely different mathematics and completely different methods to reconstruct the three-dimensional information. So I will explain this later on the following slides. So basically on the LEDs, these are the two main properties we use from them to perform phase shifting or coherent scanning interferometry. So if you use a monochromatic LED, what happens is that there is a property called the coherence length, that is how long you can displace the reference mirror and the sample you are measuring one to each other and still having interferometry properties. If the two mirrors are too far away, one from the other, what happens is that the contrast of the interference disappears, it diminishes, and you don't see them. So if this is happening, there is no way to perform interferometry. And that will be one of the main properties we will use to do this phase shift interferometry thing. On the contrary, the white LED, it has a very short coherence length. Typically, it is around 1.5 micron. And this means that if the difference between the beam splitter and the reference mirror and the sample we are measuring is more than 1.5 micron, the interference contrast is nearly disappear, and we cannot perform interferometry on that things. Okay, and with the coherence length, the coherence length is a property of how long we can separate the two beams and still performing or having contrast with interferometry. And this is directly related to the bandwidth of the light source. In that case, we see the laser that has a very, very narrow bandwidth. Typically, a laser can be less than 1 nanometer bandwidth, up to 0.000 many zeros, 1 nanometer, depending on the kind of laser. And this means that we can perform interferometry to very long distances. In fact, you can do interferometry from here to the moon by using some kind of lasers, and so on. So if we use interferential filters or LEDs, monochromatic LEDs, or white light, you can see there that the properties of the coherence lengths decreases, and the properties of the interferogram is also changing. So this is what happens if we place a kind of a sphere sample onto that interferometer, and the surface roughness of that sphere is relatively smooth or rough. So what we see here is that the appearance of the interferences changes dramatically. So on the one on the smooth surface, we can see them, we can count them. And again, going back to the previous slides, we can count with our fingers how many of these fringes we can see from side to side, and we can see, okay, there are something like 10 fringes. Every fringe equals to lambda/2, that is 250 nanometers. So 10 fringes equals to 2.5 microns. So the picture value of that sample is 2.5 microns. And because this is a microscope and I already know the magnification and the scales, I know that this is the x distance, so I can calculate for you the radius of curvature of that, just only looking at the image. But look at the image on the right. No way. It's the same radius of curvature, but the fringes, they do not have any contrast. So there is no way to perform measurements by just looking at the image. And these two kind of different samples will be the texture of these two different samples will be the ones deciding to measure with phase shifting interferometry or with white-light interferometry. So okay, in the Sensofar systems, that was a subject from the previous webinars we did. We have a micro display that displays on the field different position of the microscope, and then we have a red, green, and blue like source that is going through the micro display. Micro display in that case is totally useless for interferometry because we turn on all the pixels, so it behaves like a bright field illumination microscope. And then after that, we have a white light LED that is exactly placed after the second Q beam splitter you see here on the screen. So okay, let's go for phase shifting interferometry, how it works. So imagine you have a step height like the one we see on the first picture here. And we have the wavefront that is deriving from the optical components that are performing the interferometry thing. So what will happen is that the wavefront, that in that case is a plain wavefront, arrives to the top of the step height and reflects, while the portion of the wavefront that is still not touching the surface, it needs to travel, while the one reflected on the top is starting to travel back to the optical components. So when the second portion of the step height, the wavefront touches that second part, the first portion of the wavefront has traveled 2 times the distance of the step height. So the wavefront deformation we will achieve at the end, that is the bottom part of the slide here, will equal to 2 times the height we want to measure. So that's the reason why the phase difference will be 2 pi over lambda multiplied by 2 times the height of the surface. And then we can say that the height of the surface, that is the thing we want to measure, equals to lambda over 4 pi times multiplied by the phase difference of this wavefront. So here, the point we have to look at it is that to measure the height, we need to measure the phase difference, and we need to know very precisely what is the wavelength to do that conversation between phase and height. So how to do that? Okay, so that's relatively old technology. It's about close to 40 years now that phase shifting interferometry is applied into commercial instruments. And basically, it's going back to the equation we saw at the beginning of the presentation. So we have an intensity that equals to a background called I prima plus I second prima, that is the amplitude of the interferences multiplied by the cosine of the phase difference. And now we apply here what we call delta I, that equals to a phase displacement. So if nothing is happening into our system because we are not performing anything on it, delta equals to 0. But now we can apply a phase shift, so a displacement of anything that changes the phase. And then delta I will not equal to 0. It will equal to something. So the common ways to perform phase shifting interferometry is by using some kind of mechanical displacement, like a piezoelectric actuator that shifts the position of the sample against the beam splitter or the position of the reference mirror against the beam splitter. The quantity of that displacement we want to be exactly P over 2. And then going back to the previous equation, if we look at the height or phase difference, if we equal pi over 2, so 90 degrees phase difference, this will equal to a height difference that is lambda over 8. So this means that if I introduce into the interferogram a phase displacement of lambda over 8, we will create a new intensity that will have a displacement of 90 degrees. So by doing this 3 times, we have 3 sets of different intensities, like the ones we see here on this slide. And it's very, very, very easy to show you that the phase can be retrieved by the arctangent of this equation here, I3 minus I2 divided by I1 minus I2. So the good thing of that equation here is that the I prima and I second prima are no longer present on that equation. And this means that the nonlinearities of the sensor, optical vignetting, and anything that is deforming or changing the wavefronts is not affecting the final calculation of the phase of the phase. So that's very nice. And one of the main benefits of phase shifting interferometry is that we can achieve extremely very high resolution, like 0.01 nanometer system noise. But of course, the arctangent function is something that has a 2 pi repetition every lambda over 2, and we have no way to recover three-dimensional information if the surface is having steps larger than lambda over 2. That is more or less the limitation of that technology. So how this is done? So imagine you have a sample, you place that sample under your microscope, and then you have 3 images like the ones you see here on the screen. The first one will be the sample after placing that on the focus you want to start measuring. Second and third images belongs to a phase shift of pi over 2 or lambda over 8. That is exactly the same. So that is about 60 nanometers steps distance that are performing by shifting the position of the measuring sensor head against the sample. So, and this is the result. This is a bare silicon surface where there is a defects, some defects we want to analyze, and that defects are something like 50 nanometers depth only. So go back to the interferogram, and now sorry, to the interferometer, and now instead of using a monochromatic LED, we use the white LED, the one you see here on the screen. So now what will happen is that we have to perform, instead of several discrete steps and measuring the phase information, what we do is to acquire a set of a lot of images along the focus of the microscope. That is similar to the axial response we were explaining on previous webinars of focus variation and confocal. So the image you see here on the screen now belongs to an interferogram for a single pixel that has been taken along 10 microns along the z-axis by shifting the position of the measuring sensor head against the sample and recovering or recording one image every lambda over 8. These are the black points here. Because of the white LED, there is a general envelope of that interferogram, and that envelope will have a maximum position, and that maximum position is telling you where the surface has been best focused on the microscope and interferometer. So what's the aim of that signal? To look at that red point here. So the first thing we have to do is to measure the envelope of that interferogram. So basically there are many ways to do that, but commercial instruments and more accepted algorithmics use Fourier transform, Hilbert transform, or phase shifting again algorithms, in which at the end we discard the interferogram information and we recover only the envelope information. That is the red curve you're seeing here on the screen now. So let me explain to you one of the three. That is the Fourier transform algorithmics. That is very simple to understand. So basically, we have a signal, the one on the left, that is the interferogram. For every pixel, there is a signal like this one, in which we want to recover what is the maximum contrast position along the z-axis. In that case, it's around 4.5 micron. So we measure the Fourier transform of that signal, and the Fourier transform will show you basically the main frequency of that signal. And the main frequency is not a delta Dirac, it's a little bit wider, it's a lot more like a Gaussian, and that's because you can see that the interferogram is not a sinusoid, but it's convolved by a Gaussian itself. So the Fourier transform, you get only one of these two peaks, so you remove one of the two, and then you displace that Gaussian peak from the frequency to the zero frequency. And then doing the inverse Fourier transform, because we have shifted the frequency from the original one to the zero, the blue part, the blue components are completely disappear. So we remove the main frequency and we have only the envelope information. So again, the envelope information of that signal is an axial response. And now what we have to do is to locate that maximum position of this envelope by using a center of mass or a mathematical Gaussian fitting to that red tube. So that is a set of images, how it works. So this is a three-dimensional surface measured with white light interferometry, in which we are now seeing the interferogram on the bottom focus. That will be the interferogram seen on the top of that structure. And you can see, because of the white light properties, that there is no information on the bottom now. The previous slide didn't have any information on the top, any interferometrical signal, and that's because the height difference of this sample is larger than the coherence length of the white light source. So okay, this is a three-dimensional result, and now from that we can apply any analysis to the three-dimensional topography. So in conclusion, phase shifting interferometry is you can measure surface heights of very smooth and very continuous surfaces with sub-nanometer resolution. We are able to achieve 0.01 nanometer system noise by using that technique, but it has the problem that the vertical scanning is limited to the fraction of the wavelength, lambda over 2 in that case, because there is this 2 pi unwrapping problem, uncertainty on the equations. In contrast, white-like interferometry or coherence scanning interferometry, it can measure surface height on a smooth, two rough surfaces with 1 nanometer resolution and with a vertical scanning range that depends basically on the working distance of the objective. So you can scan several millimeters while keeping this nanometer resolution. Okay, so that's a little, again, a summary of these two technologies. So the benefits of interferometry in general is that you have excellent vertical resolution that is not depending on the numerical aperture, like we saw on other webinars, where you have a dependence on the numerical aperture. That's the case of confocal and focus variation, that you need relatively high numerical apertures to get very low system noise. This is not the case for interferometry, because as we have seen here today, the properties of vertical resolution depends on the properties of the light source, the coherence length, basically. So you have high accuracy and repeatability, and is able to measure very smooth surfaces and rough surfaces too. What's the problem with interferometry? So the problem is that if you have too much roughness on the surface, or there is too much steep angles on the surface, there is no way to see any signal that can be used to retrieve this envelope information and retrieve the Z position of every pixel. You have also problems if you have dissimilar materials like glass and metals, or optical materials in which you have phase changes, not because of the depth things or because of the texture of the surface, but you have phase difference changes because of the refraction index changes on the materials. And this doesn't mean you can measure them, but you need to know that you have these effects, because you need to correct them or to take them into account. You have no true color images with interferometry, and phase shifting, it's only working for very, very small surfaces. No way to measure sub-nanometer resolution for rough surfaces, because there is no phase information that you can retrieve this 2 pi uncertainty on the equations. So okay, let's move to the thickness measurement technology by using interferometry and confocal. So first of all, I would like to introduce 3 different aspects of transparent objects in which we are able to perform measurings on it. So the first one is what is called a layer and a substrate. That is the most typical case when we are dealing with semiconductor applications. The second one is a transparent plate and a sample behind the transparent plate, and some gap in between. That gap typically is air. That's the typical case when we are dealing with lab-on-chips materials or embedded electronics after a protective layer or a protective optical window. in which measuring the sample, measuring the topography of the sample after traveling through this transparent plate is not straightforward. So the third case is embedded structures into some transparent materials like bubbles in glass, in which you have also some optical effects that we have to take into account if the purpose is to measure the three-dimensional topography of these bubbles inside the materials. So today I will concentrate basically only on the layer and substrate, so the case we have on the left. And we need to do a discrimination of two kinds of transparent layers. The ones we call them thick and the ones we call them thin. And this is not fully agreed. Depending on who you talk, they will tell you that for me that is thick, for me that is thin. And other people will tell you thin is for me less than this and less than that, and so on. So if you talk with semiconductor people, placing silicon oxide layers on top of silicon, for them 700 nanometers is thick, and 5 nanometers is thin for them. On the other side, if you talk with coating paints for ships, they will tell you that for them 1 millimeter is thick, and less than 10 microns is not existing, basically. So we need to somehow to agree in a separation of thin and thick films, and the way to do that separation is basically using the wavelength as a measuring scale. So typically we say that we can separate materials and signals if we have layers that can behave 3 times away from the wavelength. So if we deal with 500 nanometers wavelength, we are talking about 1.5 micron at the end. So okay, that will be the summary. So thick films for optical measuring instruments means more than 1.5 micron, and thin films less than 1.5 micron. And this is very important because depending on the thickness of these transparent materials, we will be using one technology or another technology. So for thick films, we can apply confocal and interferometry, and I will explain now the difference between these two technologies on measuring thick films. And for thin films, we're using a spectroscopic reflectometry. I will also explain later. So let's start with thick film. So basically, you have to do, as we have been explaining on the previous webinar, even today, we have to perform a vertical scan along the optical axis by crossing the focus position of the objective, and we get two kinds of different signals depending on the technology we are using. The one on the top is the confocal signal, and the one on the bottom is an interferometrical signal. So let's explain what's happening for the two technologies. So let's imagine we have here a substrate and a layer that is transparent to the optical wavelengths, and we perform a vertical scan by using white light interferometry. So the signal we will retrieve is the one we see on the left. So there will be a fast reflection on the top of the layer, the interface between the air and the layer, that will provide to us an interferogram, and then it will appear a second tranche of interference fringes, not exactly on the interference layer between the layer, interference between the layer and the substrate, but that interference trench will appear a little bit farther away from that position. This is what we call the HM, so the measured height, while the real height is H. In confocal, the one on the right, things are completely different. So we will have a fast signal, the axial response peak on the fast surface interaction between the air and the layer, and there will be a second signal reflection, second axial response that will be appearing a little bit closer to it. So not exactly on the interface, but closer to the fast interface. Here we see on that slide we see two different behaviors of interferometry and confocal. One is providing a separation of the signal. The other one is providing closer signals between the two peaks. Let's see why this is happening. So let's start with confocal. So what happens with confocal is that when we are focusing the microscope on the top, on the interface between the air and the measuring layer, we have a real focus, that is the fast red rays. But when we are scanning along the optical axis, what happens is that the rays coming from the optical components gets a refraction. And that refraction bends the rays, pointing them farther away from the original pointing position. So they can reach the substrate position earlier than the reflection from the top. And this means that there will be a virtual reflection that will provide to us this axial response with the two peaks that they are in fact closer than the real separation of these two samples. So we know that, and by using the appropriate mathematics and the appropriate algorithmics, if we measure the separation of this axial response in blue, we are able to go back to the real height or the real thickness of the transparent layer. So that's an example of an axial response of 1.5 micron silicon oxide layer measured with a 0.8 numerical aperture and a 0.95 numerical aperture. So the thing we see here is that this 1.5 micron or silicon oxide layer is exactly at this frontier point I was talking before of thin and thick films. And because of the numerical aperture, the axial response is wider or narrower. What we see here is the signal on the left is not able to provide to us two separated peaks. So NA 0.8 is not able to measure this 1.5 micron. If we increase the axial response, if we increase the numerical aperture to 0.95, what happens is that the axial response is narrower, and because of that, we are able to see these two peaks corresponding to the reflection on the air-to-layer interface and the layer-to-substrate interface. And now we can apply the previous explanation of measuring the separation of these two peaks and apply the appropriate correction to measure the real thickness of this transparent layer. So again, this is something we saw in previous webinars. The numerical aperture is playing a huge role in confocal microscopy, because if you want to measure very thin layers close to the 1.5 limit, 1.5 micron limit we were talking before, we need to go to the highest possible numerical aperture to get the narrowest possible axial response. And this is achieved by using a 0.9 or 0.95 numerical aperture optics that belongs to 100x and 150x magnification. So that is an example of anodized aluminum layer with no dye components on it. This is about 7 microns thickness, total thickness, and you can see that because of this previous explanation, you are able to retrieve the three-dimensional topography of both the top air-to-layer interface and the layer-to-substrate interface. To get that three-dimensional measurements, we were using a 100x 0.95 numerical aperture objective. So okay, let's go to interferometry. So for interferometry, we have this fast signal of interferograms corresponding to the reflection of the air-to-layer interface. And as we saw before, we have a second trend of interferogram that is not appearing on the layer-to-substrate interface, but a little bit farther away. The reason for that is because the layer has a refraction index that is larger than 1, larger than air. And this means that the light needs time to travel inside this layer. If the layer is 1.5 refraction index, this is 50% more time needed to travel the same height. What does it mean? Imagine we have a layer that is 10 microns thick. If the layer is air, it means that it will need the same time to travel 10 microns inside and 10 microns after reflection, so 20 microns in comparison to the fast interface between the air and the layer. So there will be a 20 microns separation, and now because we know the speed of light, we can calculate the time or the phase difference that will equal to these 20 microns. But because the layer is not air, in that case the layer is, let's say, something like 1.5 micron, this means that the distance we will be seeing because of this additional time travel, it will not be 20 microns, but 30 microns, so 50% more. So we will measure a layer that in time equals to 30 microns, not to 20 microns. So that's the reason why the interferogram appears a little bit farther away from the original reflection, from the top reflection. So, but again, as we were seeing before, between phase shifting and coherence scanning interferometry, the light properties are also playing a huge role on that case. So if we have a blue LED, what happens is that because of the coherence length, the number of interferences along the z-axis belongs to several microns. That's something like 10 microns in that case. While if we are using a white LED, we have only this 1.5 micron interferogram envelope. So this means that if we have a 1.5 micron silicon oxide layer and we use a blue LED, the two envelopes of the two reflections are embedded each other, so they collapse and we are not able to separate them. So we are not able to see any signal that we can use to retrieve the three-dimensional shape of the top and the substrate. So we need to use a white LED, and the white LED or a white light is, because of this coherence length is shorter, we are able to see an envelope that is about 1.5 micron width, and we're able to separate and split the two signals, and from that we cover the envelopes and we cover this information to recover the three-dimensional topography on the top and on the substrate. So again, this is a three-dimensional topography of anodized aluminum with no dye, and we see the top topography of the silicon oxide layer and the bottom topography of the aluminum substrate. And on that case, we were using a 20x 0.4 numerical aperture. As explained before, the envelope properties of the interferometry do not depend on the numerical aperture, but only on the coherence length properties of the light source. And this means, and we are fortunate to that we can measure transparent materials by using interferometry and low magnification, because we still keep this 1.5 micron envelope width. So this is another example of a laser engraved on aluminum anodized layer, in which we are able to see the aluminum substrate and the alumina substrate on top. So in a summary, if we compare confocal and interferometry for the three-dimensional measurement of thick layers, that's more or less the summary. So what we see here is that the blue one that belongs to confocal, if the magnification is very low because of the width of the axial response, we will be able to measure only very thick layers, something like 100 microns or more than that. But on the other side, if we want to measure thinner and thinner layers with confocal, we need to use higher and higher magnification to get higher numerical aperture and narrower axial responses. But again, as any technique, we can see that there is a bottom limit and a top limit for every objective. And the reason for the top limit is because every time we are focusing through a transparent material, there are some optical effects that decreases the usable amplitude of the axial response, and there is a point where this amplitude is so low that we are not able to see anything. So for instance, 150x, if we are focusing through a transparent material that is 5 micron thickness, it is really difficult to see the reflection on the substrate, but it's very dim. It's very dim. So 100x or 50x are not able to measure so thin because numerical aperture is lower, but on the other side, we are able to measure thicker because the signal is still usable. And finally, if we go to the extreme, that is a 5x, we are able to measure very thick things like 5 millimeters thickness, but of course, very thick materials. So depending on the final application, you can choose within that range. On the contrary, if we look at the interferometrical ranges, that is the purple bars here, we see that any one of them starts at the same position. So you are always able to measure this 1.5 micron thickness because of the coherence length properties, and interferometry again is not depending on the numerical aperture properties. But on the other side, we see upper limit, and the upper limit is again the same as confocal. The reason for that is because every time we focus through a transparent material, there are some optical aberrations that appears because of this focusing, spherical and coma and other aberrations are appearing because of this focusing inside the materials, and the contrast decreases, and that contrast is completely destroying the information inside the material, and that is creating this upper limit. What's the base for that? 5x. 5x interferometry, it has a very low numerical aperture, and this means that these optical deformation are very weak, and because they are very weak, they preserve the contrast of the interferogram inside these materials. So we are able to measure up to 100 microns thickness by using a 10 or 5x magnification with interferometry. So that's more or less the things that have been explained up to now. And where is the limit? So the limit is where everything collapses. So when we have a very thin material that is less than 1.5 micron, what happens with interferometry is that the signal of the two envelopes collapses and we are not able to discriminate them. And for confocal, again, the same, the two peaks collapse and we are not able to get any information. If this is happening, we have to go and change the technology, and that is a spectroscopic reflectometry. So this is the real form thin films. So a spectroscopic reflectometry is a very well-known technology. It's not something new. It's something in the market like 30 years or even more than that. And basically what happens is that when we are illuminating a surface from the top, there will be a reflection and transmission of a light inside the material. When the light is transmitted, it will be arriving to the substrate and then reflecting. When this reflection arrives to the interface between the air and the layer, there will be again a transmission and a reflection. The reflection will go back to the substrate, and the substrate again will reflect back to the interface between the air and the layer, and again it will refract and reflect, and so on. And this is happening many times. So what happens is that all that reflections from the top, any one of them is carrying a phase information because the time travel inside the transparent material. And that phase difference, they sum up and interfere. And that interference will change its states depending on the properties of the layer. So the picture we see here on reflectivity that belongs to a silicon oxide is a very good one to explain that effect by changing the thickness of this transparent material. The substrate on that case was bare silicon. And what we see here is that if there is no thickness, that is the blue line, what happens is that there is only reflection, and because there is only reflection, there is no interferences between these multiple reflections. If we apply 300 nanometers silicon oxide layer on top of that silicon, there will be a change on the interference state depending on the wavelength we are using. And this is because the refraction index of this transparent material is not constant along the wavelength, but is changing. So there will be a wavelength at 425 nanometers on that case, in which these multiple reflections, they sum up and they create a constructive interference. And there is another wavelength that is the 575 nanometers, in which the addition of these multiple reflections, they get a destructive interference. So they sum up like a negative, or let's say the minimum reflection, and so on. So every wavelength will have a different behavior because of refraction index is changing along the wavelength, it's not constant. So on the past, if you wanted to measure the thickness of this transparent material and you didn't have computers, people were using just exactly the wavelength that was creating the minimum and the maximum. So if you look at this picture here now, and we see that there is a minimum at 575 nanometers, we can tell you that this belongs to lambda over 4. You remember the previous equations in which constructive interference was happening every lambda over 2 and destructive every lambda over 4. So if we have 575 nanometers and we have lambda over 4, we have to look for the following minimum, and this will be the wavelength difference divided by 4 will be this 300 nanometers thickness. On the other side, if we increase the thickness of the transparent material, what happens is that this reflectivity picture changes, and this is because the time needed to travel inside the material now it's longer, it takes more because of this thicker material. So that's the summary of this spectroscopic reflectometry thing. So changing the thickness changes the behavior of reflectivity. So let's see if we can recover the thickness by looking at this picture here. So a little bit of equations, not so complicated. So the first thing we have to know is what is the intensity, the real reflectivity of my surface. And to do that, we need to know what is called a reference material. So we use, for instance, silicon, in which we know very, very, very well, very precisely how it looks like the reflectivity on silicon. And this is because the physics of silicon are very well known. That will be the blue curve we see here. So we start on the picture on the left, in which the properties of the light source we are using, we don't know them. We call them I0, and we don't know anything about them. But we know, or we can measure by using a camera, I1, that is the reflectivity after the light source is being reflected by this silicon. Because we know very well the reflectivity of silicon because we can retrieve them from physics, and we measure I1, we can know how it looks like I0. So now let's put our sample we want to measure. Let's say something like silicon oxide on top of silicon. And again, I0 will be the same. And we know now how it looks like I0 because we did a calibration before. Now we measure I2. So the reflectivity, that is the thing we want, will equals to I2 divided by I1 and multiply it by the reflectivity of my reference material. So by doing this, now I have the reflectivity of the sample we are now measuring. And that reflectivity will be something like this. The orange curve or the gray curve, we don't know exactly, still we don't know exactly which one of these is. So let's go And let's do iteration on mathematics. So if you give me a given thickness, refraction index, and extinctions, that is the properties of the material, we can calculate how should be the reflectivity of the surface. This is a theoretical calculation, and there are many different ways to measure, to compute that reflectivity. There are different mathematical models like the Cauchy model, the Selmayr, the Lorentz, and using the Fresnel equations. And for the other side, we have the reflectivity. We have it measured by using this technique here. So we compare them. And that comparison will match by changing one of these parameters. On that case, we change D, that is the quantity we want to measure, and we change the until there is a perfect match between the theoretical reflectivity and the experimental reflectivity. When this match is happening, then we provide the measured thickness of the material. So that is an image of the software we have implemented at Sensofar, in which the yellow curve belongs to the measured reflectivity on a reference silicon sample, and the blue curve belongs to the measured reflectivity on a silicon oxide layer. And the least square function is a function where the x-axis changes the thickness of the mathematical model compared to this reflectivity thing, and there will be a minimum, and that minimum belongs to the real thickness of the surface. That on that case is close to 500 millimeters. So that is an example of a measurement in two different positions of thickness measurements. We are able to measure down to 50 nanometers layers, up to 1.5 microns by using this spectroscopic reflectometry thing. Acquisition time is about 1 second. And we can evaluate that thing in a single pixel up to an addition of several pixels together. So that is more or less depending on the magnification we are using, down to 0.5 micron pixel size. Okay, so of course, like any other technology, there are some drawbacks, and one of them is that we can measure only one layer, and this is an indirect method. So improve if the thickness range is known. So you have seen that the mathematical curve, it has showing several minima, and you need to know which one of these minima is the one that is corresponding to your surface. Typically, they are separated hundreds of nanometers, so most of the times there is no chance to fail on that. Okay, so this is my presentation for today, and many thank you for your attention. So we are now open for questions.